Okay, so last class, what you have seen is to look at this time domain signals in another way. That means to look at the Fourier domain, right? So in Fourier domain, basically we have seen what are called the Fourier series and the Fourier transforms. Essentially, they are the same with slight differ. I mean, conceptually they are the same. So if you have a time domain signal f of t, then I can represent it using weighted sum of the cosines and its harmonics, or sines and its harmonics, or in general, weighted sum of the complex exponential, right? We have seen all this stuff. And when you add all of them, basically you can switch back between these two. Either you can use f of t, or I can equivalently represent f using the coefficients n or dn, right? Which is called the Fourier representation, or an in terms of complex exponential. And if the function is not periodic, then you can go for what are called the continuous transforms, or basically the Fourier transforms. So here, instead of the summation, it is replaced by an integral. So here, if you look at the second thing, you can see that f of t is equal to 1 by 2 pi. Integral will come here. And then f tilde of omega are the coefficients like cn and dn. And then comes the complex exponential, right? Like an e raised to I omega n. Now here, the idea is that the frequency is not discrete. Here it's like omega 1, omega 2, omega 2, omega 3, like that. But here it's continuous. So there is a d omega here, and the summation is happening continuously, right? So it's a continuous spectrum. Here it's a discrete spectrum. So that's a difference. And then we have seen how to look at this sine wave and how to do the filtering. And then we reached up to the point where we are doing the 2D Fourier transforms. So we have defined the 2D Fourier transforms by extending it into 2 dimensions. And then we looked at the 2D Fourier transforms, right? So essentially, if you look at an object, which is 1 inside a circular region and 0 outside it, like what you have represented here, then I can take a Fourier transform, 2D Fourier transform of this object using this formula, which is nothing but the extension of one-dimensional Fourier transforms. And then I can do a low-pass filtering. So if I do a low-pass filtering, basically I am filtering out the high-frequency contents, and only low-pass is passed, because it's a filter with 1 being in the center and 0 outside. So that when you multiply it, only the lower frequencies will be retained, right? And that will give me a smooth image. So here, for Fourier transform is nothing but f of uv, where u corresponds to the Fourier variable corresponding to x, just like t and omega. Similarly, v corresponds to y. And then you do the filter, and you will get different features can be extracted. And then if you want to really do it experimentally, rather than looking at looking it as a mathematical object, you can do as an experiment with a simple convex lenses. So they take 2 convex lens of same focal length, and then you can actually make this lens do Fourier transforms for you, 2D Fourier transforms. So if you are interested in doing this experiment, you can actually buy things from Amazon and do by yourself. Just search for 4F imaging systems, look at the design, and get things from Amazon, and you'll be able to actually see the Fourier transform of these objects. Exactly this object you can do. If you are interested in it, you can contact me. We can do it in our lab, or you just approach the UG lab in the physics department. They will be able to demonstrate this for you. Similarly, we can take his photographs and again do it mathematically in a computer. Just do the Fourier transforms, low pass filter it, and then you can extract the smooth features, extract the edges by doing a high pass filter, right? Now we are going to look at the application of the spatial Fourier transforms, basically in MRI and computer tomography. So if you look at this application in computer tomography, so we have already seen that. So we have already seen that there are ways. So the measurement in computer tomography is P theta of t, right? The projection data, and from the projection data, basically we have to reconstruct the absorption coefficient. And we have done a method called the back projection, where we are projecting back the data to the object domain and then rotate it and keep adding it. That will give me some image that we have already seen. But the main problem with such images are they are basically blurred images, because I told you that this is actually a convolution operator with 1 by r. How it is coming, I didn't tell you. But basically blurring is synonym with convolution, right? So if you want to remove the blurring, basically you have to do deconvolution. But that can also be handled using Fourier transforms. So Fourier transform is another approach to computer tomography to make reconstructions better. So one way to look at it is, I have already told you that we have a projection data P of t at each theta, that is P theta of t. What you have to do is you have to take the Fourier transform of this data. Now t is not the time, that you have to keep in mind. T is a spatial variable, which is the distance of the X-rays from the origin. Now with respect to this variable, you can take a Fourier transform. That is one-dimensional Fourier transform, because for each theta, this is a one-dimensional function. So you take the Fourier transform corresponding to t, which give me an omega variable. And if you take the Fourier transform, then one can see that this Fourier transform is in fact related to 2D Fourier transform of the absorption coefficient. Now, what is absorption coefficient? It's a tissue property. Now, it's a function of both x and y for a 2D slice of the object that I have already told you. It can be 3D as well, but we are considering only 2D slice. Now, this is the absorption coefficient of the 2D slice of the object. And if it is a two-dimensional function, definitely we can try to think about taking Fourier transform, 2D Fourier transform. So if x, u is the Fourier variable corresponding to x and v is the Fourier variable corresponding to y, then if I take the 2D Fourier transform, it will look like this. So minus integral minus infinity to infinity, mu of xy, all this stuff. This is essentially the same stuff we were discussing. Now, what does Fourier slice theorem tells you is that this 1D Fourier transform of the projection data is equal to 2D Fourier transform of the object restricted to a line. So 2D Fourier transform of the object is also a two-dimensional function. So if I plot u and v here, basically 2D Fourier transform is a two-dimensional function. But this is just one-dimensional function. So if I want to equate it, basically it is just a cross-section of this two-dimensional Fourier transform. So that people have seen that, basically, in fact, we can prove that 1D Fourier transform of the projection data is equal to 2D Fourier transform of the object at a same angle. So this is taken at a given angle. You will also get the 2D Fourier transform at a given angle. What does it mean is that from the measurement and its Fourier transform, we were able to get an information about the object Fourier transform, which is a nice thing. So if I keep changing my angle, I will be able to get more and more Fourier transform data of the object like this. So if this theta is small enough, I will get almost all the Fourier transform data of the object itself. That means Fourier transform of the mu of xy. So if I get the 2D Fourier transform mu of xy, how do you find mu of xy? You take the inverse Fourier transform. So that's how we can get into a reconstruction using Fourier transform. But now what is the advantage of doing this? Why don't you just do the back projection? So the advantage is that, as you know, the back projection is corrupted with this blurring. Here, I can get rid of this blurring by doing a filtering. So once I get the 2D Fourier transform of the object like this, from 1D measurements of the 1D Fourier transform of the measurements, then I can do whatever filtering that I want, just like what I have done here. So I am getting this one from my Fourier slice theorem. If I get this one, basically I can do this type of filterings to do whatever I want and then come back. Then do the reconstruction, inversion. That will give me better images. So those images are shown here. These are very simple reconstructions, and you can see blurring is removed to a certain extent. Of course, there are artifacts associated with the Fourier transforms, numerical errors, but otherwise it's more or less good one. Now we are going to look at what is application of Fourier transforms in magnetic resonance imaging. So I have already told you that Fourier transform has got applications in computer tomography. It has got applications in microscopy. Microscopy is basically Fourier optics. The resolution limit of microscopy, right, like that, right? So, and I have already told you 4F imaging system, like how lenses can actually do Fourier transform. I just mentioned that you just search 4F imaging system. And in fact, 4F imaging system is also a crucial part of microscopy. So Fourier has got a lot of applications in bioimaging. And one such example is the famous magnetic resonance imaging, which works on the principle of Fourier optics. It is the heart of this principle is basically Fourier optics. Sorry, not Fourier optics, Fourier concept of Fourier series or Fourier transforms, right? So in the human body, there are in different molecules like water, fat, there are a lot of hydrogen atoms. And each hydrogen atom has got one proton inside the nucleus. right? And this gives you a positive charge. And this proton actually spins around an axis, which gives a magnetic field around it, like a small bar magnet. Okay, when I say spin, basically we are going to depict it as something which rotates, like a spinning top. But that is not how it actually is. Basically, it's essentially a quantum mechanical phenomenon. So if you want to really learn the theory of MRI, you should know the basics of quantum mechanics. But there is a classical mechanics approach to MRI based on what are called the Bloch's equations. But I'm not going to cover any of those here, but I will just qualitatively tell you what is it and what it has to do with Fourier transform. That is my aim. So here there are so many hydrogen atoms, and each hydrogen atom has got a proton and it spins. And because of the spin, it has got and it is charged, and hence it has got a magnetic field. And this magnetic field like a bar magnet with a north and a south pole. So these are very tiny magnets in the body, but the problem is that these are distributed in the whole body, and these bar magnets are basically randomly oriented. That means if you look at the neck, suppose they are not randomly oriented, they are oriented in a nice way, then our body will act as a magnet, right? Because all the small magnetic moments will add up to get an entire net magnetic moment and a net magnetization, right? So that I will be every human body will be like a magnet. We may be able to attract something, but that is not the case. So the net magnetization is basically zero because of this random orientation. Of course, I mean, when I say even if it is not randomly oriented, the field may not be that strong to see, but even then there will be a finite magnetization we will be able to measure. But that is not the case because of random orientation. So the question that they are asked is, can we use this particular field to do something? Is this field, magnetization field, if it is oriented in a correct direction, will it give some physiological properties of the body? So the answer is yes. So first step in this direction was to align these tiny magnets from its random orientation to a given direction. If we can do that, then we can try to manipulate it to generate some signals from the body, right? So in order to do that, what they did is they applied a huge magnetic field into the body that is called B0 field. So this is the first magnetic field being used in the MRI. It's a huge magnets you might have seen in the MRI pictures. So this field will ensure that all these randomly oriented small bar magnets are going to be aligned like this. So these are the proton, and these are called the small bar magnets being randomly oriented. Then I'm going to apply a field, roughly something like 1.5 to 3 Tesla, which are common permanent magnets being used in this type of MRI machines. Then you will see that most of these bar magnets will align along the B. Not all of them, but most of them. Now, in order to get a picture of what is going on, you assume that there is a spinning top. So the spinning top is rotating here. So it is just rotating on its axis. Now what happens? It is rotating at a given angular velocity omega 0. Now, suppose after some time, because the gravity is acting on it, it will try to topple, right? So what happens here? You can see that there is a reaction force. So this spinning top, if it will exert a force to the ground, and there is an equal and opposite reaction from the ground to up, right? It depends on how much weight it is giving down. It will give a force to up. At the same time, the weight will also act from the center of mass to down, which is where the gravity is acting. So these two forces are equal and opposite. So they form a torque. Because of this torque, what happens is this spinning top will start processing. So you might have already seen that in your childhood when you play with the spinning tops, it rotates, but when it tries to fall, basically it will not just fall from top to bottom like that in a plane. Basically, it will start rotating along this axis as well. So there will be two rotations. One is rotation and another is precession, right? Now, suppose this spinning top is made of magnet, and when it is falling because of gravity, suppose I put a coil near to this XY plane, then you can see that when it precesses, basically because of this precession, it will induce a voltage in this coil, right? Because of electromagnetic induction. When there is a magnetic field being changed in a coil, that will induce a voltage. That's basically the basic principles from this field theory, right? So you will get an induced voltage here based on Lenz's law. so that that voltage is proportional to the frequency of precession. Right? That is exactly what we are doing here. I mean, not exactly. I mean, this is the analogous situation with which we can actually learn what is happening in MRI. So essentially, in order to mimic this gravity, we should have another field. So these are like a rotating spins are like the magnet being oriented along the B. Now I want to have this precession. So I will apply a B1 field, a field created by a radio frequency pulse. So this is not a permanent magnet, but it's an electromagnet. But this field will be applied perpendicular to this B0 field so that this particular spinning top will go down to the XY plane. So now it is aligned along the Z axis. But when this RF field is applied, it will go down and start rotating in the XY plane. So that is exactly what being shown here. So each bar magnet, due to the higher proton in the hydrogen molecule, forms a magnetic moment, and in a given magnetic moment density gives you a net magnetization, which is now aligned along B0, which is the main field. But when I apply an RF pulse or a RF electromagnet, which is perpendicular to this field, then this magnetization will tip so that all the bar magnets will tip to XY plane. But when it tips, it just doesn't fall like this, but it will start processing like this in a spiral way. And it finally falls to the XY plane, and in the XY plane, it starts rotating. Now, I'm not going to look at the spiral rotation. I don't care right now about that. I'm only going to look at how this vector start rotating in the XY plane. So that is being shown here. So we already know that a vector rotating in this XY plane can be represented in terms of e raised to minus j omega t, which we have already seen, where the magnitude is m0 and it rotates with respect to omega as the angular frequency. In our case, this magnetization is equal to m0 e raised to minus y omega 0 t, where omega 0 it depends on the initial field B0, the main field, using this relation where gamma is called the gyromagnetic ratio. So only thing that you have to remember is omega is a function of B0. Larger the field B0, larger will be my omega 0. Now I have put an R here inside the brackets, which is to indicate that, look, this M0 depends on the magnetization of the hydrogen, the proton induced magnetic field, right? This bar magnets. Now the concentration of hydrogen molecule can be different at different parts of the body. So this M can be different at different parts of the body. So in order to indicate the spatial dependence of this M, I have put an R here, and it is also a function of time. So that's why you are getting this signal and this relation. Now, one thing that you have to keep in mind is this omega 0 t is gamma B0 t is, this relation is valid only when the field is a constant field. So the main field, that big magnets, there's 1.5 Tesla magnets which orient these randomly oriented protons in one direction, that magnet is basically assumed to be a constant magnet. But if I add a gradient to this magnet using some electromagnets to it, I'm going to add a gradient to it. That means I'm going to change this magnet B0 as a function of both space and time, like an additive quantity. So I am going to have a B, which is equal to B0 plus delta B, where B0 is a constant, our old permanent magnet, but then there is a gradient to it which can change with respect to time and space. If you add that, then I have to change this omega 0 t to be omega 0 t corresponding to B0 plus gamma times integral 0 to t delta B dt. If you want to know why this is coming, you can just put delta B is equal to B0. If I put delta B equal to B0, this B0 is a constant, I can take it out, and this will become t. So it will be gamma B0 t, but gamma B0 is omega 0, which is omega 0 t. So this particular thing will go to this one when delta B is a constant field. Otherwise, it's a general term. So with this general term, I can put my main magnetization of this form. M0 e raised to I omega 0 t e raised to minus I gamma 0 to t delta B, right? I got all this stuff. Now, this guy is now rotating in the XY plane, like a spinning top falling to the ground and rotating in the ground, where I have put the coil like this, right? This guy will fall to the ground, it start rotating in the ground where I have the induced voltage, right? So this magnetization is now rotating in the XY plane, and there is an induced voltage in the coil. That induced current or the voltage is called S of t, my signal, right? So now we are going to look at what will happen to that signal. That's what you are going to look at. So this S of t is nothing but in double integral m of xy e raised to minus this form. That means this particular rotation is going to induce a signal for me, and that can be expressed of this form after certain approximations, which I am skipping. So essentially, there is two things happened. One thing is that this e raised to minus omega 0 t is vanished. That I can filter out. I don't care about omega 0 t. I'm interested only in this part. Why it is so, I will tell you. Right? So I will only look at this part, but e raised to minus I omega 0 t, I can filter out. Now, why there is a double integral over here? So the idea is that this coil is kept near to my hand. So for example, if this is my hand, I have kept the coil near to here. And after applying an RF pulse, all this magnetization will start rotating in this plane and it will induce the voltage here. Everything is fine. But then the problem is, from which part of my hand this signal is coming from? Is it the proton near to the surface? Is it a proton deep inside the tissue? From where it is coming from? Right? So we don't have any idea from exactly which point the signal is coming from. In fact, the signal is coming from a bulk part of the tissue. So that's why we have to take a volume integral here. So here it's an area integral because we are looking at two-dimensional slices. As I told you, all my examples will be 2D. If it is a three-dimensional like m of x, y, z, this integral should be dx, dy, dz. It's a volume integral. That means the signal, the single signal that we are considering here, which is r, basically will be added up from each r in a volume, and that has to be, that should contribute to my SOT. That means there is a double integral or a volume integral depending on dimensions, right? And this is my signal that I am getting. Now still there is a problem. You are talking about B0 field, that is fine because we are making the hydrogen molecules oriented into one direction. And then we applied an RF field, that is also fine because we want to flip it like a spinning top so that the flipped magnets will start inducing a signal in the coil. And our expectation is from this signal, we will be able to find out the physiological status of the body, physiological or anatomical status of the body. That's our aim. But then the problem is we introduced a delta B over here. What it has to do with all these problems? So the idea is that if this delta B is not there, essentially what you are going to get, this signal is just a volume integral. Suppose this is 0 or a constant, then this equation will correspond to only this part. Then this is equal to just an area integral of m of xy. So I will get just one number. With that number, what will I do? So I will get some bulk information from a volume without telling from where it is coming. So we have to basically spatially resolve the information coming from the tissue so that I can say, look, I can create an image like an MRI image of your head. In MRI image of a head, it will tell you where is what, right? That spatial information is embedded as an image, like a picture. But here, all the information is coming from a volume is converted to a number. That will not work, right? So we have to basically map each information from where it is coming to a point in my picture so that I can say, look, this information is basically the cerebrum. This is basically my cortex. That way we can, upper cortex, if it's a frontal lobe, I can tell all those things by looking at the picture, like a one-to-one map, right? So in order to do that, we need this field. So this is basically helps you to map spatial information one-to-one between the actual object and the image so that we will get an actual image of the object, right? So to do that, we have to design this system, and that's basically the MRI engineers do. So basically this delta B, I'm showing you very simple stuff. So delta B can be written in the form, I told you delta B is a function of both spatial coordinate and time. Now I'm going to write it in the form AX plus BY, where X is a spatial variable X, Y is a spatial variable Y, but A and B are functions of time, where it is Gx of t and Gy of t. If I write delta B of RT of this form, then I can substitute it back to my equation, and I can redefine my gamma times integral 0 to t Gx of t d tau as Kx of t, and similarly for Gy of t as Ky of t. So if I consider these two, then you can see that this is nothing but m of xy e raised to minus 2 pi x kx plus y ky dx dy. Now what is this? Basically, it's a 2D Fourier transform of your magnetization. That means 2D Fourier transform of your tissue property. So essentially what you have achieved here is we were able to get my signal S of t as a 2D Fourier transform of your object function, tissue property. which is the most powerful thing that can happen. We are basically getting the 2D Fourier transform of the object from a time domain signal measurement. This is basically time factor that is coming here, right? That's the so this is the power of MRI. Now, what will you do with the 2D Fourier transform? Fine, you got it. What will you do? So, in order to understand that, you have to look at kx of t as u and ky of t as v, right? U corresponding to Fourier variable of x, v corresponding to Fourier variable of y. So you can put this ux and vy here. So it's become ux plus vy, exactly the 2D Fourier transform. But if you want to have all u and v, right? If you want the information of all u and v, basically you have to change ks of t and ky of t. If you change kx of t, u will change. If you change ky of t, v will change. So depending on u and v, I will get the whole Fourier transform of the data in my through my signal. So if you want to change that, basically you have to change kx and ky. That is exactly being done in the MRI. So that when I change kx and ky, basically I'm getting the 2D Fourier transform of the object. So once you get all the 2D Fourier transforms of the object, basically I can take an inverse Fourier transform to find the tissue property. So this is the MRI about. But of course, there are other finer details. Like I told you that this particular magnetization is spiraling and coming down to the bottom, and then it is rotating. But it will never keep rotating there. It has to go back. When you remove the RF pulse, it will go back. Now, how it goes down and how it goes back, and what are the time scales involved? Those things are very important, like relaxation times and all those things, which I cannot take. This is itself is a bit cruel to you because it's just 15 minutes of MRI. So just what you have to remember is this particular Fourier transforms are very handy in MRI. Fourier transform are the basics of MRI. Fourier transform is very useful in CT, although it's not quite natural to it, but it is useful in CT. Fourier transform is inherent to microscopy. If you want to learn microscopy, you should know Fourier transform. There is no way around, right? And microscopy is the basics of biology. So Fourier transform is nothing new to biology. I mean, without Fourier transform, I would rather say, biology exists, but we cannot see the biology. We can see the biology because of microscope. If you don't know Fourier transform, we cannot see it properly. So Fourier transform is very important for biomedical engineering. You can see a lot of numerous examples in other branches of engineering as well. So just remember when you learn Fourier transform in other contexts and then try to relate it to the biomedical engineering principle. So in a nutshell, there are three fields. One is the main field to align the protons in the magnet, like what I've told you in the beginning. And then you have got a radio frequency to flip it, like gravity, what gravity do to a spinning top. And then there is a coil to, and there is a gradient field to localize the information. So we have to make sure that the signal coming from head is actually mapped to head in the picture, right? That localization has to happen. For that matter, we use a gradient field. And when you use the gradient field, you will see that the signal has got a structure of 2D Fourier transform of the object data. So if you properly design your signal, then you will be able to basically get the 2D Fourier transform of the object, from which I can take an inverse Fourier transform to find the actual object. That's how the MRI generates images. So these are some examples of some gradient fields you try to understand by yourself. So I'm going to skip it. So now we will move to the next part of the course. So can you see the slides?
Yes, sir.
Yeah. Okay, so now we will look at the second part, which I told you that we will be looking at what are the signals that are coming from the body, like ECG and EEG. So the fundamental idea is that the body itself is generating some electrical signals, right? So these electrical signals have to be can be measured, and how now the question is how these electrical signals are being generated. That's the first question that you have to ask, and then the question of how to measure it and how to use it for diagnosis or the inverse problems purpose, right? That's a point. So I'll be just telling you quickly how these Fourier transfer, sorry, how these signals are being generated in the body. And while telling this, my aim is just to tell there are many engineering concepts that are coming in this particular picture. Basically, these are electrical signals happening in a body, and this branch of science is called electrophysiology. And I'm going to just give a very glimpse with two lectures on how things are coming. If you want to really learn this particular subject, basically you have to look at some other courses. For example, Professor Rohit Manchanta, Professor Neeta Kanekar in our department are offering these courses in a very detailed manner. So you can have a look at it. Now, please don't think that this has nothing to do with electrical or electronics engineering. Especially electrical electronics has a lot of a lot of contributions have happened from that branches of science in engineering in this particular field. We can actually represent our electrical networks or these electrical sources in the body using resistors and capacitors that you already might have seen in your +2, right? And which you will be covering in more detail in your engineering. So we can basically use resistors and capacitors to model biological processes. So that's a beauty of this particular subject. So we will give I'll give basically a trailer of this subject. You can have a look at it, and there are so many informations that are going to come here. Just try to remember some of them, and when you see your actual electrical engineering, then you try to relate it to this particular problem and try to take more advanced courses on this topic in the coming semesters. So this we already explained. So we are going to look at the origin of these signals from the body, and as you may guess, this electrical activity has its origin from the basic building block of the body, which are the cells, and the cells groups together to form the organ. So and the organ do all sort of this movement. I mean the functions to make the homeostasis, which you already see, right? Basically, essentially, it's to make the body stable, right? So this cell comprises of a nucleus, and then you have got some membrane. See, that's the idea of all these things. Everything is protected. So the whole body is protected by the skin, and then you have got a skeleton to protect the organ, most of them, right? And several layers of immune system to protect against intruders. Everything is protection and security, nothing else, because you have to keep the keep our working things working. So it's about stability. So here, even at the lower level, you can see the protections. See, the cell membrane, and then cell membrane has got something inside and outside. What is inside is intracellular region, and outside is extracellular, or sometimes called cytoplasm inside regions. And then there is a nucleus. It again has got a nuclear membrane, and then nucleolus and all our DNA, RNA, all those stuff comes inside, right? So now the question is, it has got a barrier, right? It has got a cell membrane. So we are interested in a couple of things based on the cell membrane and how different substances cross to and fro the cell membrane, either coming from outside to inside or from inside to outside. And that is important for us to learn the electrophysiology. That part of the cell is what we are looking at in a not in a detailed fashion, but up to a certain extent, right? So this particular cell, so this cell has got mostly water, and there are several ions which are very important for electrophysiology. They are called sodium, potassium ion, chloride ion, calcium ion, many of them. And these are diluted in the water, so they form electrolyte. So both sodium, potassium, all these ions can be either inside or outside the cell. They can move across the cell, right? Then comes the blood. The blood plasma is outside, right? Then blood plasma, it contains RBC, it contains different hormones, it contains the nutrients being absorbed from the guts, right? It contains oxygen to be delivered to the cell. It contains carbon dioxide to be taken away from the cell for expulsion. All these things are there outside the cell. Now, these materials have to come out, these materials have to penetrate. So, for example, nutrients, right? These nutrients basically what are the fat, carbohydrates, and the proteins, which will be converted to fatty acids, glucose, and the amino acids. And these guys have to penetrate into the cell so that the cell will convert it into energy. right? All these things will happen. Oxygen has to go inside the cell. Ions have to move to and fro from the towards to and fro the cell, from the cell, right? So all these things have to be happen through the membrane, and this membrane is very tricky. It is very selective to certain ions. It is very selective to certain substances. It will not just give free pass to anything. The gates are not open. Most of the gates are always closed. Not always, mostly closed. So under certain conditions, gate will be opened, otherwise it will be closed. There are certain activities going on. This is like a security, very high traffic is going around these gates, but it's not easy. But that way you have to view this problem. So these are the things that I have already told you, like a circulation system here. So the heart has got two pumps. One is to pump the oxygenated blood. Oxygenation happens in the lungs, and that particular blood is being pumped through the aorta to arteries. So arteries, and then arteries switch to basically the arterioles and to the capillaries. From the capillaries are present near to all the cells. From the capillaries, all this transfer of materials, oxygen, nutrients, everything happens to the cell. And from that, the deoxygenated blood will be carried from the venous, venules, and then from the venous back to the heart, and it will be pumped back to the lungs. And in the lungs, basically oxygenation happens. CO2 is being released and oxygenation happens, and it comes back to the next part of the heart. So how a heart works, we will be covering it in the next class. But this is how the circulation happens. And some of the blood has to go through the guts to collect the nutrients. Some of them has to go through the kidney to excrete, say, for example, urea from the blood, right? Some of them has to go through the liver to store some of the nutrients, right? So these are the general idea about the circulation system. Now we will see how these electrical signals originate from the cell. So for that, as I told you, we are interested only in the cell membrane. And so we'll just give some quick idea about how that part of the cell. Say, for example, in the cell, you know that it's completely full of water. I think these things have been taken in the first part of this course. So it's mostly water and electrolytes, because there are so many ions being dissolved in the water, and water is present both outside and inside the cell. And the cell membrane, as I told you, it's a physical membrane, right? It should have some supporting structures. So these proteins, there are two proteins. One is the structural proteins and another is the globular proteins. So structural proteins, they group together to form what are called long filamental type of structures called tubules. These microtubules are actually can group together to give a structural stability to the membranes. But globular proteins are basically used as gates in the membrane. So these globular proteins are attached to the cell membrane so that they act as a gate. So these materials can pass through this gate. Now this membrane is composed of what are called the lipids, especially the phospholipids. This membrane is basically bilayer phospholipids. They are mostly insoluble in water, and this particular membrane has got this globular proteins attached to it, which acts as a gate, right? So these things we are going to see. So in our case, we are interested in this cell membrane. We will see how it looks like. And then we are also interested in what are called mitochondria. Now, this mitochondria is very important because these are energy production units inside the cell. So this mitochondria has got oxidative enzymes. What does it do is, when the nutrients like glucose, fatty acids, and amino acids enter the cell, like what we will see, it actually do some oxidative reaction to convert it into carbon dioxide, water, and energy. And that energy will be stored inside the cell. And whenever it is required, it will be released. And this is very important for electrophysiology. So mitochondria, some fundamental idea we will learn, and then the rest of the things are not very important for this particular module. All right, so let's look at the function of this mitochondria. So as I told you, the heart basically pump this oxygenated blood through artery to through aorta, which is the biggest vessel, and then that branches to arteries, and then to arterioles, and then comes the capillaries, and capillaries are present near the cells, like here. And from the capillaries, this glucose, fatty acids, and amino acids will enter the cell. Now, this is the mitochondria, and all the three will be converted to what is called acetyl coenzyme. how it is converted and all those things are very complicated biochemical reactions, which we are not covering. But we are just looking at the fundamentally what is happening. I mean, the very qualitatively what is happening. So this acetyl coenzyme will be converted to carbon dioxide, water, and energy by use of inside this mitochondria. Now, how does it do it? It is doing so now. See, now there is an energy being released in this process because of this oxidative enzyme. Now, this energy will be it will be utilized to convert what are called adenosine triphosphate, some compound here, to ATP, which is called adenosine triphosphate. So this energy being released because of the oxidative reaction upon the nutrients by the mitochondria, that energy will be utilized to convert ADP to ATP. So when the ADP is converted to ATP, that amount of equivalent energy is actually stored in ATP because you need energy for this conversion. So that equivalent amount of energy is stored in ATP. So if you want this energy back, basically you have to initiate a conversion from ATP to ADP so that energy will be released. So this is basically how the energy is stored in the cells from the nutrients that we are eating, extracting from our food, right? So this particular process is called basically the energy conversion, and ADP and ATP are called the currency converters inside the cell. So if you want energy, you convert ATP to ADP. If you want energy to be stored, you convert ADP to ATP, like that, right? And this is very crucial for our case. We will see that. Now this carbon dioxide and water will be expelled. The carbon dioxide will go back to the blood. It will either make a bond to the blood cells, or it will just get dissolved in the blood, and it will be taken by the blood back to through the veins to the heart, and it will be pumped to the lungs, where the carbon dioxide will be released and the oxygen will be attached, which is basically oxygenation process, and it will be circulation will be continued. Now we will see the cell membrane again back. So this is a lipid bilayer. So you can see that there are two layers for this lipid, and there are some globular proteins which are attached to it. Some of the proteins will protrude from the outer of the cell to interior, whereas some of them are just at the periphery. Now these proteins are going to be the gates that I was talking about. So the materials are trying to go from inside and outside. So they need a passage or a gate, and these proteins will act as a gate for this particular movement. So we are going to look at a couple of such gates and what all things can be passed. Now the question that we have to ask is, what are the things that are going to pass? So three things that we are going to actually look at is basically that, of course, all these things are present inside and outside the cell, and their concentrations are given here. Extracellular fluid means outside the cell region. Intracellular fluid means the fluid inside the cell. And this is, you can consider this as a cell membrane, and the concentrations are given here. So for example, sodium is abundant outside the cell, whereas it is less inside. Potassium is very less outside, but it is very large inside, right? So, I mean, why is it so? There are certain reasons for that, which we will get an idea when we go for the other slides. So now we are going to see what way these particles can actually go from and outside this to cell and outside the cell. What are the processes involved? So you can see that this forms a lipid bilayer, and these are the globular proteins, and this acts as the gate that I told you. Now, two ways in which this particular movement can happen. One is diffusion. So diffusion is nothing but you just imagine a very crowded bus. So you are inside the bus and it's really crowded. And when it stops in the bus stop where you want to get down, you can get down in the bus stop quite easily, because when you try to go out of the bus, people are basically relaxed, and they may even push you out, right? Because you are going from a higher concentration region, which is the bus, to a lower concentration region, which is nothing but the bus stop or the outside region. That's exactly what is the diffusion is. Basically, diffusion happens always from a higher concentration to a lower concentration. There is a concentration gradient. Gradient means what? Higher concentration minus lower concentration, right? The difference, difference with respect to the spatial variable, you have to take a differential, but basically it's a difference. That difference will dictate you how fast you can move. So suppose there are 1,000 people being packed into a 400 square feet room, which is closed, the doors are closed, will you be able to, the moment the door opens, you'll be just trying to run out, right? So this pressure is so high that you'll somehow try to go out, because otherwise you'll get suffocated, right? So the more the package is happening, more the concentration gradient. The more the concentration gradient, the moment you open the door, there will be a higher influx, outflux from the room to a low concentration region, right? So here the same thing, the concentration dictates how fast things can move. So simple diffusion can be two types. There will be simple diffusion as facilitated diffusion, but both are actually from a higher concentration to a lower concentration. You do not have to spend any energy. It's a natural. It will just flow from a higher concentration to lower concentration. Now, simple diffusion can happen across the lipid bilayer. It can just, some materials can just pass the lipid bilayer, but some of them cannot do that. That depends on what is called the permeability of the lipid bilayer to that particular substance. But some of them can be passed through the protein channel. But then this channel is not always closed. Here it is shown as open, but it is not always open. Sometimes it is closed and it can be open sometimes, depending on certain conditions. So when it is open, basically it's a watery channel, so that simple diffusion can happen through the watery channel. Another option is a facilitated diffusion. In facilitated diffusion, basically the things are being transported by certain materials, some certain receptors. So these materials can attach to these receptors and they will carry it and take them to the interior or outside. So this can happen to both directions. It can be from outside to inside or from inside to outside the cell, right? But then active transport is a different story. So let's take again the bus example. Suppose a bus came and it's completely crowded and you want to get inside the bus from the bus stop. Then you know the process is not easy, because when you try to get inside the bus, you have to basically push, right? And if it is really crowded, the people from inside will try to push you out. They won't allow you to get in. You might have practiced it, right? So it's the same way if you are packed in 1,000 people in 400 square feet being squeezed. Will you be able to squeeze one more person to inside? You have to put energy, otherwise you won't get inside, right? So this energy, if you want to go against the concentration gradient, that means if you want to get into a bus, basically you are trying to move from a lower concentration to higher concentration region. That is called active transport. That requires energy. And this energy is being supplied by the ATP, ADP, like what I have told you. So there will be an ATP and ADP setup here. So the moment energy is required, ATP will be converted to ADP. That energy is released and that can be used for this type of transport. So these are the things that I have already told you. Some of the examples you can learn by yourself. Now, certain things that you have to keep in mind is that how these things can actually move. So basically these movements can happen, although it's a simple diffusion. It depends on the size of the material that is moving, the size, the width of the channel that you have. So these things quantitatively can be modeled as permeability, or the permeability of the channel. So it depends on the size of the material, width of the channel, etc. Right? So depending on that, I can have dedicated channels or dedicated gates for different ions. So for example, there is called sodium gates or sodium channel. There can be potassium channels. So in the sodium channel, only sodium can move. Potassium cannot. Similarly, for potassium channel, only sodium can move. So sorry, potassium can move, not the sodium. So these are dedicated channels, and we are going to look at such dedicated channels for sodium and potassium, which is quite important for the electrical activity of the human body. So here you can see that a sodium channel has sodium, as I told you, is abundant outside the cell, and inside it is less. Similarly, potassium is more inside the cell, outside it is less. Now the sodium gate has got two doors. The one door is outside the cell, and there is one more door which is inside, which is not shown here. I will come to it. So the gate which is outside the cell is called the activation gate, and gate which is inside the cell is called the inactivation gate. Now what happens is that when, due to some reason, if this gate is open, the sodium from outside can go inside naturally through diffusion, because sodium is abundant outside, it is not inside. So there is a diffusion. can happen? Only because this gate was closed, it was not able to go inside. The moment it is open, because of concentration gradient, simple diffusion can happen. It can go inside, right? Just like what you have shown here. But at the same time, potassium, when it is open from inside, the potassium can go out because the potential concentration gradient is high inside. Concentration is high inside. So the gradient will push the potassium outside or through this gate, right? And additionally, there is a negative charge for the sodium gate so that it can attract more positive ions to inside. Now the question is, how do you open this gate? Who tells these gates to be opened or closed? So the idea is that there are two ways in which it can happen. One is called voltage gating and another is called ligand gating. So in ligand gating, in voltage gating, basically this gate will be opened or this door will be opened depending on the potential difference between the cell and the outer. So potential difference between the interior and the outer region of the cell. For example, you take a voltmeter, you put one of the probe inside the cell and one probe outside the cell. Now it will show you a potential difference between the interior and outside of the cell. That potential difference is normal. It has got a value which is normal, or it's called the resting membrane potential, which is roughly minus 90 millivolt. Minus indicates that the interior of the cell is at a negative voltage compared to outside, whose magnitude is 90 millivolt. That's how you have to read it. So the cell inside will be at a lower potential than the outside by an amount 90 millivolt. That is called resting membrane potential. That is because you can easily imagine that there are different concentration of sodium and potassium inside and outside the cell, and that creates this potential difference, right? Now, suppose this resting membrane potential, which is normal or at equilibrium, which is 90, is changed. Suppose it is, suppose it perturbs due to some reason. Suppose it becomes minus 90, becomes minus 70. Then what happens is that the sodium gate will open. See, this sodium gate can open. Similarly, this potassium gate can open. So by changing the potential difference across the cell due to some reasons, then actually I can actually open or close this gate, which can cause the sodium ions to come inside or the potassium ions to go outside. So this is called voltage gating. Now ligand gating is a different story. Ligand gating means some materials will get attached to this particular gate, which are globular proteins. When it gets attached to it, basically it changes what are called conformation of the protein, which causes, so don't worry about those things. Just assume that some materials will get attached to this, which causes this door to open so that the sodium or potassium can come in or go out. Such ligand gatings are very important in neuronal sensing, like what is happening inside. So for example, sensation of sensations, right? Touch, eyes, all these things are based on what are called neuron cells. And in neuron cells, basically this type of ligand gating happens a lot. That if time permits, we will be covering that part in a very quick way. So we have got ligand gating and power voltage gating, but right now for this particular electrical activity, we are trying to see only the voltage gating for the time being. Now this sodium channel voltage gating is what is being shown here, and sodium and potassium voltage gating is being shown here. So you can see that when the potential difference of the across the cell membrane is very high, the sodium channel will open. The activation gate of the sodium channel will open. But at the same time, and then the sodium can go inside. But when the sodium goes inside, basically it will become more positive potential, right? But at the same time, when the sodium channel is open, because the cell potential is higher, inside cell potential is higher, the same time the potassium channel can also get open. But that will happen only after a delay. So these are called time is very important in all these switching mechanisms. So with the moment the potential is very high, the sodium channel will open, the activation gate will open, sodium start going inside. At the same time, the potassium door also get the signal to get it open, but it will not respond faster. It will respond after a time delay. So after a time delay means by that time, a lot of sodium will come inside and it will increase the cell potential to a very large value. By that time, after this lazy period, this guy slowly opens the door so that the potassium can go out. By the time it's late, but that's fine. So after some time, the potassium, since potassiums are going out, but since these are positive ions and they are losing from the cell, in interior of the cell potential can come down. So the sodium potential, so sodium influx, because of this some disturbance, when it comes inside, it will increase the potential of the cell for some time, and after some times, when potassium gates are open, this will come down. So we'll see that once again after a few slides. So just keep this in mind. There is a
Sir?
delay between sodium and potassium channels. Yeah, please.
Sir, can you once again explain voltage gating?
So voltage gating is simply, see, look, this is basically a sodium. This is a ligand, lipid bilayer. This is a cell membrane. Outside, I have it denoted it as a cell outside, and inside is a cell inside, right? This is cell membrane. And these are the globular proteins which acts as a gate. Now, the idea is that this sodium is abundant outside and it is trying to come inside, because the concentration is very high here. There is a natural tendency to come inside, but it can never come inside because the gates are closed for it, and it cannot diffuse through the lipid bilayer because it's not permeable to lipid bilayer. So only way is this gate has to get open. When it will get open, only there are two options for that. One is voltage controlled opening. That means I will put a voltage to this. Just assume that this is an electrically controlled door. I will put a voltage, the motor will act and it will open. Just imagine that. That's enough for you right now, right? And another option is if I stick something to it, this will open. That's called ligand gating. Some materials, when you stick to this one, this gate will open. How it is being done, all these things you can learn in higher courses. Especially ligand gating is much more involved. It requires a lot of biochemical reactions are involved. So it's a very involved subject. Right now, just treat it like a door which has got a motor connected to it. Depending on this the voltage difference between the interior and outside of the cell, this door can be opened or closed. That's how we have to view it. So if the potential difference of the cell, now in resting membrane potential means inside the cell will always be always be at a lower potential than the outside by an amount 90 millivolt. That means the potential difference between inside and outside will be minus 90 millivolt. But if it becomes a minus 70 millivolt, that means the interior of the cell is having higher potential. The potential difference between them are decreasing. Then this door will open and sodium will come inside. At the same time, potassium will also get a signal to open this door. But this will not do. This is a lazy door. It will not react to the signals abruptly. So it will take some time to open. So by that time, a lot of sodium will go inside and it will increase the cell potential to a larger value. But that is momentarily, only for some time, because after some time this gate will open and sodiums will be lost from the interior, so that we are losing positive ions. So that will ensure that this momentarily high value of potential will come down, right? That's how this happens. So facilitated diffusion, I already told you. So this is something now we are going to look at this potentials, right? So I told you the factors that affects the net diffusion are basically the permeability of the membrane. So how fast, how permeable the membrane are actually to the some material. So for example, if you look at the permeability, basically it depends on the channel into its resistance. So the larger the resistance of the channel, the lesser its permeable is. And it's also inversely proportional to molecular weight of the material. If the material is, or the ion or whatever is very big compared to the channel, essentially it will not be fast, right? So permeability is inversely proportional to the molecular weight. It is inversely proportional to resistance per unit channel, right? But it is directly proportional to number of channels. If there are large number of channels, there is a chance that it can be fast. So it is directly proportional to number of channels. So permeability is something that is important. It can vary for different materials. Then difference in concentration, which you have already given you examples. Pressure difference, of course, when the same material is there in one of the region, there will be a lot of pressure, and that can cause a movement. And another important thing is the potential difference. See, these materials, suppose I am talking about materials which are being transported like sodium, potassium, etc. They are charged particles. Suppose we are not talking about any charged particles. Suppose we are just talking about inert materials, which doesn't have any charge, neutral particles. Then there will never be any question of potential differences or anything, right? Here, when the charges are being distributed out of the concentration gradient, essentially the potential difference is also happening. Suppose I take 100 sodium ion and try to squeeze it into a small region, the positive ion, positive charge in that small region will keep increasing. So if I want to push one more ion to that region, basically I have to oppose two things. One, the concentration gradient, and another is potential electric field, right? Because there is a high positive field coming from there. And if I want to push one more charge to that region, essentially I have to put a work. I have to do some work to actually do that. So two things are opposing me. One is the concentration. I am moving from a low concentration to high concentration. And another thing is I'm also moving against the potential, right? So that's exactly what the active transport do. In active transport, the energy is spent not against just the concentration gradient, but also against the potential gradient, because here the moving particles are actually charged. So you have to always respect the potential differences as well, not just concentration gradient. If these were neutral particles, we only have to worry about the concentration gradient. So taking into all this mind, you have to look at all these processes. This is exactly what I've told you. Now, we are going to look at this active transport. As I told you, active transport is something which will try to push something against the potential gradient or against the electrical gradient, right? It's uphill. If you want to climb the hill, you have to spend energy. But if you want to just come out of the slide down the hill, it is the gravity will help you, right? So essentially, here we are moving away from you are trying to push things against something. So you need to spend energy, and that there exists such active transport here. And one such example is the sodium potassium pump. So if you look at the sodium potassium pump, basically this sodium potassium pump, we have to basically pump sodium from inside to outside. See, that is a bit difficult because sodium is abundant outside and less inside, and now you are trying to take more sodium from inside, which is already in a very low state. You are taking more from outside inside and trying to push it to outside. So you are moving it against the potential gradient, and not just the concentration gradient, not just the concentration gradient, but against the potential gradient, because it's already the so many potential so many positive sodium ions are already here, and you are still trying to push them to outside, right? So how it is being done? Again, there are some receptors interior of the cell, sodium receptors interior of the cell, and potassium receptors outside the cell. The interior of the cell will connect. It has got three. This receptor can connect 3 sodium ions, whereas the potassium receptor can connect up to 2 potassium ions. And what happens is, whenever this pump is activated, there is an energy conversion happens, so that ATP is converted to ADP. That energy is released. This energy will cause this receptor to take 3 sodium ions to outside. At the same time, it can take 2 positive ions to inside, potassium ions to inside, right? So essentially, 3 sodium ions is lost from the cell, 2 potassium ions is gained by the cell, so that effectively it loses 1 positive charge. So you can roughly, and it also loses one. Effectively, it loses a substance and it also loses a charge. That's a essential idea about one cycle of sodium potassium pump. And what is the use of this that we are going to see? So for example, in osmosis, essentially I told you these organelles inside the cell, most of them are negatively charged, and this will try to attract the positively charged particles inside the cell, so that at some point the concentration of the materials inside the cell will increase. But as I told you, water is present both inside and outside, and the water can diffuse through the lipid bilayer. So water is everywhere. Now this has become an electrolyte where most of these substances are basically in one part of the semi-permeable membrane. Basically, the concentration is very high, whereas on the left side, the concentration is less. Then what happens? Either these particles have to diffuse through the semi-permeable membrane to the left side, but that is not possible because of permeability issues. Then only option is that the water has to go outside to inside. That is called osmosis. So when water goes inside, The problem is the water will increase the pressure of the material cell inside, which can cause the cell to burst. So who is saving us? Again, sodium potassium pump. So when this happens, because of osmosis, the pressure inside the cell increases. The sodium potassium pump will get activated, so that it will remove three sodium to outside and 2 potassium to inside, and effectively one particle is lost from inside the cell. So that will causes the concentration to comes down, so that the osmosis will be removed, stopped. So that is one advantage of the sodium potassium pump, but we will also see this is important for electrical activity. So coming back to this problem, as I told you, you have to respect not just the concentration gradient, you also have to respect the potential gradient. So suppose let's take one example, sorry, one by one. So let's take the potassium case. So the potassium is trying to go from inside to outside because the concentration of potassium is very high here. So when the potassium gates are open by simple diffusion, this potassium can go through the watery channels to outside. But can it go, can it keep on going so that the concentration of the potassium will come to zero? That will not happen, because it again go along the concentration gradient. At the same time, when it goes out, the ions which reaches the outside will try to oppose it, because there is a positive charges that is accumulating here that will try to oppose the incoming one, so that there is a potential gradient that is also happening here. There are positive charges here and correspondingly there are negative charges here. This is potential difference happening which tries to oppose it, right? So there is a balance between this concentration gradient and the potential gradient, so that the concentration gradient will dictate you how much voltage is being induced here. That is called Nernst potential. So I can calculate the Nernst potential assuming that only sodium is going here, and potassium is going here, sodium is not present. Similarly, I can calculate the Nernst potential for the sodium case assuming that potassium is not present. If you do it independently, assuming that the other is not present, you can use what is called the Nernst potential here, which is equal to the voltage induced by this movement due to concentration gradient or simple diffusion is equal to minus 61 log Ci by Co, where Ci is a concentration inside and concentration outside. So basically the difference will tell you how much is the induced voltage. Now, if you calculate it just for potassium, assuming that sodium is not present, you will get it as minus 94 millivolt. Whereas for sodium, you will get plus 61 millivolt. Again, you have to read the sign depending on, I am measuring it inside of the cell with respect to outside. Minus 94 minus indicate that inside the cell it is at a lower potential. Outside it is, and for plus 61 means it is cell is at a higher potential compared to outside region. But I have already told you that the cell potential is at minus 90 millivolt. So none of these two are actually telling the exact potential inside or resting membrane potential or the equilibrium potential of the cell. But you can see that the potassium value is more closer to the equilibrium value, because it is minus 94 millivolt and the actual one is minus 90 millivolt. Then people thought about, okay, we have to change the model. This is not going to work. And they found that, see, you cannot take this model, because when I say K plus is going outside, and because of the outside K plus trying to oppose it, we are trying to reach the balance. But when the sodium is also present here, it is not the K that is going to oppose. I mean, the potassium that reaches outside, only those, not only those things will oppose, but also the presence of Na plus will oppose it. So both Na and K plus outside will oppose this moment. Similarly, both K plus and Na present inside will oppose this moment. So you have to take into account of that coupled effect, which will give me a new equation, what is called Goldman equation. And that is given here. And if you calculate using the Goldman equation and from the table that I have shown you earlier, you can see that the negative potential will now be equal to minus 86 millivolt. So now the potential difference that we have calculated for the cell is minus 86 millivolt, but that is also not true, because we have already measured it and what you are getting is minus 90 millivolt. Now the question is, what is happening? There comes again the sodium potassium pump. So the theory is that the sodium potassium pump is actually working on it, and it will give me an additional minus 4 millivolt, so that minus 86 minus 4 give me minus 90 millivolt. And this minus 4 millivolt corresponds to 3 sodium outside and 2 potassium. sorry, 3 sodium yeah, 3 sodium outside and 2 potassium inside. So this corresponds to that voltage and it compensates for this minus 4 volt. So finally, what you are getting is the Goldman's equation along with the sodium potassium pump gives you the exact rusting membrane potential. So the idea is that this potential can be modeled using Nernst equation. So this basically this can act as a forward model for our problem. So this is the quantified version of the phenomenon that is happening. But still we didn't tell about the electrical signal. So these are potential differences that is happening. But why these potential differences are measurable using a probe kept at the chest or kept at the head? From where these guys are coming from, that you have to see again. Right. So this is essentially what I have told you. So because there is a movement of charged ions across the cell, you can see that there is a charge redistribution happening across the cell membrane. So if you look at the cell membrane, there are plus sign here, there is minus sign here, similarly minus and plus. So across the cell membrane, there are charge redistribution, which you already seen. So this is a thin cell membrane and there are charges, opposite charges being accumulated on both sides. Naturally, this acts as a capacitor, like a parallel plate capacitor, right? So then this particular capacitor, so this particular phenomenon can be basically modeled using capacitors, right? And the movement of the ions across the channel, I told you, depends on the resistivity or the permeability of the membrane that can be modeled using resistors. So essentially, all these phenomena can be modeled using resistors, capacitors, in some cases using diodes. So, and then you can write down all the networks. You can use your KCL, KVL, whatever Kirchhoff's voltage or current law. I think you might have studied in +2, right? All this electrical network analysis can be done to learn biology. That is the whole idea of electrophysiology, right? So that's something which you should remember. So please do Professor Manchanda's course. He will give a complete idea about how to do this type of analysis and how engineering principles can be used for this. So in fact, if you look at his group, there are so many engineers who are actually working on his problems. So you can have a look at those courses. Now we are going to come back and see what are called the action potentials. That means the potentials that are being generated inside the cell. Almost most of them I have already told you, but we can once again look at it. So I told you that these are dedicated sodium channels. These are dedicated potassium channels. A sodium channel has got 2 gates. One is the activation gate, which is outside the cell. There is an inactivation gate, which is inside the cell. And potassium has got just one channel, one gate, which is inside the cell. Now, as I told you, the rusting membrane potential is minus 90 millivolt. But suppose when you touch the body, and when you are in cold temperature or hot temperature or some sensation, basically these sensations can cause a disturbance in the rusting membrane potential from minus 90 millivolts to say minus 70 or minus 50 millivolts. Due to some external disturbance, this particular potential will move from minus 90 to say minus 70. The moment the interior potential of the cell is large compared to or increased compared to the outside from the resting value, this activation gate will open. The moment activation gate will open, sodium will start flowing inside. But I told you, the moment activation gate for the sodium is open, the signal is fed to the potassium gate as well. But this lazy guy will open only after some time. By the time a lot of sodium will come inside, this sodium will push minus 90 millivolt to plus 35 millivolt for some time. So that the gate, the potential inside the cell now will become plus 35 millivolt. That it will become more positive compared to the outside. See? Now what happens is, by the time it reaches plus 35 millivolt, this gate will open and the sodium will start going out. At the same time, this gate will be closed. That means the sodium inactivation gate will be closed, so that further coming of sodium is stopped. At the same time, potassium start going out. So this together, this will ensure that from plus 35 millivolt, the potential now will come down because we are losing positive charge from the interior, so that this potential will keep coming down till it reaches minus 90 millivolt. Only when it reaches the minus 90 millivolt, this gate will be open. Otherwise, it will keep closed. So that once it reaches minus 90 millivolt, it will be ready for the nest action, and this particular thing is called action potential. So this is what is depicted here. In the beginning it is at minus 90 millivolt, but then suddenly because of some disturbance it reaches minus 70 millivolt, but then because of this sodium channels opens and the sodium start coming in slide because of this large influx, the potential reaches plus 35 millivolt, and then you can see that the potassium gates will open, sodium is inactivated, so that charge is lost from the cell, so the repolarization, so that the potential is coming down from plus 35 to minus 90. So this increase of potential inside the cell due to the sodium influx is called depolarization, and the decrease of the cell potential from plus 35 to minus 90 is called the repolarization. So this is called the action potential. So these are the signals being generated, and these signals are being responsible for communication between the cells. Why you are feeling your senses of touching, seeing, everything is based on these concepts. Of course, there are slight differences when you look at the cardiac or when you look at the neuron cell signaling. Slight differences are there, but most of them, this is how it is working, right? So this this particular method, this particular process is actually a positive feedback. So you can see that when one of the gates, suppose due to disturbance, the inside the cell will become positive. When it becomes positive, more positive, one of the sodium gate channel will open. Then sodium will come inside. But when sodium comes inside, the cell will become more positive, because now see, you can see it going up towards plus 35. So when it becomes more positive, nearby sodium channels will also get open. So it is a cumulative effect, like an avalanche effect. So nearby sodium will channel get open and more sodium will come. When more sodium comes, again the nearby channels have to open because it becomes more positive. So this is a positive feedback where we are pushing from a resting state to an unstable state. But it will not last there, because this particular process is called Hodgkin cycle. This is a positive feedback that is happening inside the cell. But after some time, what happens is repolarization. So this can be viewed as a negative feedback. The moment this happens, then suddenly the potassium channels will activate. It will try to flush out some of the charges so that it will try to push it to the stable state. See? So this is one example of a negative and positive feedback that you can look at in this one. Now the question is, how does this propagate? So for example, when you touch at the hand, we are basically sensing it with the brain. So the signal has to go to the brain, then only we will sense it, right? So how does this propagation happen? So if you look at this nerve fiber, you can see that suppose at the center. So in the first A figure, there is no action potential happening. In B, there is an action potential happening at the center. So that interior will become more positive compared to outside. But when interior becomes more positive, it will actually trigger more sodium channels to open in the neighborhood, so that it will slightly spread, as in C, right? But then these will trigger more and more sodium channels in the neighborhood, as in D. So this spreads, the depolarization spreads like this. But then by this time, the repolarization should happen at the center, because this is within that time interval, the repolarization should be initiated here. Then that will start happening here. So when repolarization happens, the cell will become like A. So in the middle part, it start becoming A, but towards the edge, it is like still depolarized and it will start traveling. So this is how this process gets in traveling. Now this is a method actually to measure this action potential. This is a very good example of the instrumentation. We have actually looked at the instrumentation amplifiers and all those things in the tutorial 1. So here what you do is you take a differential amplifier and connect two input. One is the output voltage, output or extracellular region, and another is the intracellular region. So this is the extracellular and this is the intracellular that is given to this differential amplifier. Right now, if this potential difference be measured here, so this amplifier will tell you the difference between the cellular membrane potential, right? Ideally it should be minus 90 millivolt, but we are doing an experiment. Now we are going to put it into another differential amplifier, and I will put the voltage that I would like to have between these two probes. So I would like to have a potential difference between these two probes, which will be set here. So for example, I want to have a potential difference of a minus 30 millivolt between these two. That means between extracellular and intracellular. If you want to have like that, essentially we can put that value in this one. So if you put that value, then the output of that amplifier will be non-zero only if this is not equal to this. Suppose this is equal to this. If the preset desired value and the actual difference between the cell membrane potential are the same, the output will be zero, then everything is fine. Suppose they are not the same, then the output of this amplifier will not be zero. It will inject more ion current, which will adjust it in such a way that this potential will be kept. This will be clamped to this desired value. So this is a negative feedback circuit called voltage clamping. And by this method, I can change this voltage and study what is the current that is required to keep this. So ion current versus voltage can be measured using this method. And this is the first experimental setup with which all this electrophysiology was measured. People tried to understand what are action potentials. It's a very classical experimental setup. You can look at the wiki and learn it. And another thing is that, as I told you, every time we are having an action potential means the sodium is going inside and potassium is taken out. There is always a redistribution of charges. Suppose there are like 5 lakh action potential happens. After that, there will be a redistribution of ions and the cell will become inactive, unable to do any further action potentials. In such case, against the savior comes basically the sodium potassium pump. So sodium potassium pump will again work. It will take 3 sodiums out, 2 sodium in, again redistribution happens and this cell will be ready for the next action potential, right? So it's basically the recharging. So sodium potassium pump are very, very important for this type of things. So this is basically a Nernst equation derivation. If you want, you can have a look at it, but I'm not going to cover. So if you have any questions, you can ask, otherwise we can stop.
Sir, like here we have a lot of information in the slides. So like what kind?
Sorry, I'm not able to hear you properly. Can you louder, please?
Can you hear me now?
Yeah, please.
Yeah, so I was asking that we have a lot of information in the slides, formulas and stuff. So like what kind of information are we supposed to, learn for exam? Because like
I mean, basically, for the exam point of view, basically, you have to just, I mean, you don't have to learn the names or anything. See, for example, I won't ask you what are these equations and all those things. I will not ask you to expand adenosine diphosphate. I will not give you some numbers to find out Goldman equation. You don't have to by heart Goldman equation. You don't have to look at the EMF generated. I will give you C0 and CI. You have to calculate EMF. Those things I will not do. I just want to get an idea about what is going on. Conceptual level. Say for basically it's a basic. Sorry. Sorry. Hello. Who asked me this question? Can you please? Hello. Can you please talk? Okay. Any other questions? Anything? Okay, so if you don't have anything, let's stop. So are you hearing me? Hello?
yes, sir, you're audible.
Yeah. So you asked me the question, right? I mean, about the. Hello?
Yes, sir. I asked, but someone else unmuted. His audio was disturbing.
Okay, fine. So did you get the point?
Yes, sir. I got it. Yeah.
Yeah. So only things, whatever things that I told you, just watch the video. That should be enough to do the exam. I mean, you don't have to by heart any of these jargons or anything. Get the idea of the concepts. I will give multiple choice questions. The answer will be there in the choice. Only thing is, if you have the idea, you can answer it so quite easily. And I will send you a couple of more practice examples, questions with answers from this topic. So you'll get an idea what sort of things that you have to learn. That's it. Okay. So I think I don't think any questions are there, so we can stop. Yeah. Thanks.